My name is Konstantinos Michmizos. I'm an assistant professor of computer science at Rutgers University, where I direct the Computational Brain Lab. In this talk, I'll tell you a few things about how we endorse our robots with some of the brain's most remarkable learning abilities. The von Neumann paradigm is already having more than its fair share of inefficiency, too much its brilliance. As our systems were designed with feasibility, not efficiency, at their center, the explosive growth of AI and mobile robotics is actually limited by the current efficiency of our computing systems. With Moore's law soon to be outdated, there is no better time than this to reconsider the feasibility of new solutions. What we need is an infrastructure that is versatile, robust, and power efficient to handle these seismic shifts in our computational needs. And what we have now is enough knowledge on how the brain can achieve these goals. The brain is fault tolerant. It is also extremely power efficient, and it performs self-learning, which is perhaps the most important attribute. We've been developing brain-inspired controllers for robots exploring unknown dynamic environments. And we've given measurable evidence that our approach is more robust and orders of magnitude more energy efficient compared to deep learning. We've developed a spiking actor-critic architecture that combines the advantages of the two worlds, the energy efficiency of a spiking network and the high performance of deep networks. To do this, we developed a hybrid training algorithm on top of a deep reinforcement learning framework that we call spiking deep deterministic policy gradient, or STDPG. The problem with STDPG is that it works great for environments that have low dimensional observation and action spaces, where we do not need to fuse too many sensory signals or choose between a large set of possible actions, which is exactly what we need to do in a dynamic environment. The reason why our method would fail in a dynamic environment has to do with the limited resolution of the spiking neurons in representing information. And in high dimensional tasks, the optimality of the control policy depends on the encoding precision of the input and output spaces. The need for real-time processing makes things even worse, as the neurons have now even less spikes to represent a continuous value. To improve the resolution, we used a key attribute in the brain associated with efficient computation, population encoding, the use of populations of neurons to represent information, where each neuron in a population has a receptive field that captures part of the encoded signal. So we developed a population-coded spiking actor-critic network that now can learn optimal solutions for high-dimensional control tasks. We trained our method using deep reinforcement learning algorithms, both on policy and off policy. This covers the whole spectrum of reinforcement learning and demonstrates our method's general applicability to policy gradient-based deep algorithms. Given a deep reinforcement learning method, we can now generate a spiking counterpart that has the same performance while being orders of magnitude more energy efficient compared to deep learning. We allowed Intel's neuromorphic chip Loihi to interact in real time with the OpenAI gene, and we benchmark our neuromorphic method in 4 environments with the most rich and unstable dynamics. We evaluated the rewards gained, and we got the same level of exceptional performance compared to the deep network approaches. For some of them, we did even better. We also looked at the energy consumption, where the neuromorphic approach consumed 140 times less energy per inference compared to the deep networks. The takeaway message of this slide is that adding more neurons to a population encoding and allowing the receptive fields to be learned result to better learning. So what have we achieved? Quoting one of the reviewers, in addition to providing a spiking deep reinforcement learning framework that is now orders of magnitude more energy efficient than the mainstream deep learning approaches, the main contribution of our work is that it becomes a great starting point for researchers who want to start exploring and exploiting spiking networks for deep reinforcement learning. And this concludes my